Hello, my name is Peiyun Hu. I'm going to talk to you about our work on exploiting visibility for 3D object detection. What is a good representation for 3D data from sensors such as LiDAR? We visualize a LiDAR point cloud of a city street from a bird's eye view. We highlight two regions that may contain an object. Because nearby points look similar, convolutional architectures with local receptive fields may struggle to distinguish these two regions. But 3D data from sensors such as LiDAR provides more than just point measurements. They also indicate that rays emanating from the sensor to each 3D point must pass through free space. Visualizing such free space through raycasting, showing grain, makes it much easier to distinguish these two regions. We now can see that a partially occluded vehicle might exist in the left region, but likely does not exist in the right region. Representing LiDAR data as XYZ points fundamentally destroys such free space information. In this work, we introduce a simple approach for incorporating free space reasoning into 3D object detectors. First, we point out that existing representations for LiDAR processing tend not to reason about free space. Point representations such as PointNet might destroy such visibility information when normalizing input point clouds. Voxel representations, such as point pillars, employ convolutional architectures that are designed to be translation invariant, which could also destroy visibility information. Interestingly, visibility reasoning is quite common in applications such as robotic mapping, which often reason about occupancy and free space. Our work combines such classic schools of thought with contemporary 3D deep network. Let's begin by revisiting contemporary deep voxel architectures. We start by discretizing the point cloud using a voxel grid. Then we encode each voxel based on the points that fall into it. Finally, after reshaping, we have a deep voxel representation, which is essentially a multi-channel feature map. Now we have described the underlying deep voxel representation. We introduce a simple approach to incorporate visibility. We start by performing raycasting over the voxel grid. This produces a visibility volume, which can be sliced into 2D images at different heights. These slices are then concatenated with the multi-channel feature map. The result is a visibility-augmented deep voxel representation. We can perform raycasting efficiently through voxel traversal. As we look at the animation, the key intuition is that by figuring out which edge the ray exits, we know which voxel the ray will enter next. This allows the algorithm to focus on only the voxels that are intersected by the ray. Once we perform raycasting over all the 3D points and aggregated the results, we will have a 3D visibility volume as shown on the right. So far, we have introduced how to compute visibility over a single LiDAR sweep. One crucial property of state-of-the-art 3D detectors is temporal aggregation. That is, such detectors do not process a single LiDAR sweep, but an aggregated sweep that consists of multiple LiDAR frames, which typically produces a denser point cloud. Given multiple sweeps, we borrow ideas from occupancy mapping such as Bayesian filtering, which allows us to efficiently compute multiple frames. Finally, another crucial modification in state-of-the-art 3D object detectors is object augmentation. State-of-the-art methods insert virtual objects copy-pasted from other LiDAR scenes into batches of LiDAR sweeps. It is particularly useful to virtually insert rarely seen objects such as buses. However, naive copy-pasting often violates scene visibility. By raycasting, we can figure out how to insert virtual objects in a visibility-consistent fashion. By augmenting visibility into state-of-the-art deep voxel representations, we're able to improve point pillars by 4.5% in overall MAP. In terms of individual classes, we see over 10% improvement on the most common class cars. We also see almost 20% improvement over buses and trailers. If you are interested in learning more about this work, feel free to check out the website. Thanks for watching.